Perhaps as you know, there are 3 PWRs and 6 BWRs, or 4 different generations. And I would just, before I start my presentation, make a comment with respect to the first presentation this morning where there was figures about plant-like extraction. Also in Sweden, the licensees are planning for long-term operation between 50 and 60 years. But these are the licensees' plan. As well as in France and other countries, this has to be assessed and decided by the regulator. So, I will give some degradation experience from Swedish nuclear power plants. And also then continue with how we regulate and supervise aging management in Sweden. And I will also reflect something about long-term operation. And as already been said this morning, when we speak about aging, we speak about physical aging, technological aging, but also other forms of aging. Aging and analytical methods and techniques, regulation and guides and standards which are not updated to present knowledge and experience, but also aging of personnel and organizations. There have been some discussion this morning of the classical bat tube curve, which of course could be seen as a principal design basis for a nuclear power plant and its different systems, structures and components. And with the basic safety principles to use proven design, we hope that we get few initial failures, then a period with no or even less failure, and then with good margin against fatigue, wear and tear. So this is as a principle. But if we now look at what have we seen so far in the countries, if we look at the Swedish experience as well as experience in other countries, then we have a completely different picture. Speaking mostly about the Swedish experience, we saw that already in the end of the 1970s, there began to be failures in small piping in nozzle due to vibration fatigue. And this is, of course, in some form of design failures, because with proper design there should not be vibration, but it's really hard to predict vibration. In the end of the 1970s, beginning of the 1980s, they got a report from Sweden as well as in reactors in US of the stress cohesion cracking in small piping of austenitic wrought steel, but also in stimulated tubes made of nickel-based alloy. And when we come to the middle of the 1980s, the end of the 1980s, then there was a lot of reports of stress cohesion cracking in larger pipings, as well as flow-assisted corrosion in secondary side PWRs, and also thermal fatigue, in particular BWRs, but also some of the PWRs. And then we come to the end of the 1990s. We saw reports of incident of interdendritic stress corrosion cracking in welds made of nickel-based alloy, particularly in the BWRs. And early in the 2000s, we have seen incident of primary water stress corrosion cracking in nickel-based alloys in PWRs, but also some signs of stress corrosion cracking in what is called a nuclear grade material. And that is a material with low carbon content, which was used to replace other part of piping which previously had been there had been stress corrosion cracking. So this is a picture that is completely different to what we predict. And here are some data from the OECD NIA worldwide piping degradation database, which show you that what I just said, that in the period of the end of the 1970s to mostly in the 1980s, where there was a lot of stress corrosion cracking throughout the world. And coming back to the pictures, every time there have seen problems of, for instance, stress corrosion cracking thermal fatigue and so forth, measures have been taken by replacement of affected component, but also change of operating condition, change of water chemistry. So experience is continuously feedback and lead to action taken at the plant, and we as regulator require such actions. And here are some figures of the most frequent degradation mechanism that we have seen in Swedish nuclear power plants. And it's not the classical fatigue, which could be predicted by the bar tube curve. But the most of the crack is intergranular corrosion cracking, other form of corrosion cracking, which was not foreseen during the design phase. And there also have been a lot of thermal fatigue, which could be affected by change of operating conditions. But we have an extensive in-service inspection program. And as you can see from this picture, nearly all, 94% of all the degradation that have been observed in the Swedish reactor have been detected by in-service inspection in a very early phase before there have been any major safety consequences. Around 5% have been detected by leak detection, other small portion by walk down and other means of detection. If I turn to us as a regulator, we have a strong legal basis and we issue binding regulations. And among them we have requirements for agent management. And in particular, we have very stringent requirements on in-service inspection and in-service testing of pressurized component and other safety-related structures. We're now in the process to revise and precise our regulation in the view that the licensee are planning long-term operation, as I said. So we have to clarify certain aspects of aging management, particularly in the terms of time-limiting aging analysis, which will be important when we, somewhere down the line, will take decision about long-term operation. And as I said, we have a very stringent requirement on the service inspection. I will not go into all details on this picture, but we require the licensee to have a very systematic approach to assess all the system structures and components in the plant, whether or not they could be susceptible to different degradation mechanisms, and also taking into account the consequences of different types of failures. And then to determine inspection target, inspection intervals, and have a good process to qualify inspection techniques so we have reliable results. And then a systematic feedback. And according to our requirements, the licensee have to update the in-service inspection program every year based on experience, both in their own plants but also in other plants. And we as a regulator, we review the licensee's aging management program, and we supervise the licensee aging management activities, which include also their resources, their competence for aging management. But we also have a system with different type of independent inspection bodies that on a more detailed level supervise test, inspection and review results, and also have a system with independent qualification body that qualify both personnel and inspection system. So coming to long-term operation, this is challenges for both licensees and regulators. And we have, as regulators, has worked together within the OECD Committee of the Nuclear Regulators Association, where all of the European regulators, as well as many other regulators throughout the world, to discuss what are the challenges for us as regulators and what are the different approaches. And as already been said this morning, there are different approaches. In US they have a formal process, a license renewal process, since they have a time-limited license as a basis. On the other hand, in most of the European countries, the licenses are not limited in time. So our conclusion or recommendation from the CNRA is that if you don't have a license that is limited in time, questions about LTO have to be processed to periodic safety review. And this is what we will do in Sweden. So, but going for long-term operation, the licensee's organization, resource and expertise must be adaptable to manage new safety issues that might be rise during the long-term operation. And this also applies for us as regulators. But the basis is, of course, the thorough knowledge of all the different degradation mechanisms is essential. And what we can see so far, that research activities and operating inspection worldwide have led us to a situation where we now have a good knowledge of different degradation mechanisms and the different aspects, how they can affect component and structures. But we must continue both with further research, with proactive materials degradation research, and we also have to follow up and make detailed damage analysis every time we see signs of degradation. Because based on those damage analysis, we get to know more about different degradation mechanisms, and that also how we as regulators can require the licensees to take action. And it is very important that we continue the international cooperation. As perhaps some of you know, the International Atomic Energy Agency had continued work started within US NRC, the US regulators, with generic aging lessons learned. They extended the program, so they now have a good database and have started to produce reports with international experience of generic aging lessons learned, and also to continue within the OECD with degradation databases. So, to come to a conclusion, that effective aging management had to be taken into account, even from the design phase, which means that when you design replacement components as well as nuclear power plants, you take into account all the knowledge that we now have on different degradation and aging mechanisms, and also make the different structures and components inspectable throughout the planned period of operation. And in our evaluation of potential for long-term operation, aging management will be necessary. But as already been said in several presentations this morning, it is not sufficient. We have to consider other aspects also. And this is, of course, what safety improvements have already been implemented in old plants, and what are the need for additional safety improvement. And also how the licensee learn from operating experience, and how the licensee ensure that they have enough resources, and we have to evaluate their performance, and also finally the security of the plant. Thank you.